Hey, let's talk about metallic bonds. This is Dr. B, and it's occurred to me that when people discuss metallic bonds, there's a little secret that they typically don't reveal. Other forms of bonding, such as ionic and covalent, are beautiful in that they explain nicely how each element wants to obtain a noble gas configuration. They do so by losing or sharing electrons. I get it, it's wonderful. Metallic bonds are clearly very strong. I mean, I'm looking around this room and I see big, strong metals everywhere. They seem to be among the strongest. And yet, what's going on? It's usually explained as a mobile sea of electrons. Fine, but is anything obtaining a noble gas configuration? I mean, if the metals are losing some electrons, who's gaining? Apparently, nobody. So it's worth taking a minute to try to understand these in a little bit more detail. I think if you listen or read to other explanations, they'll simply talk about this mobile sea of electrons, but they won't discuss whether they're getting noble gas configurations or not. And I think that's important to consider. So let's begin by agreeing that metals can easily lose electrons. They all have two valence electrons. They're going to lose them. The d block underneath, if it exists, is going to also play a role, but typically they're losing electrons. Fine, so you get a cation and an electron. If they're all lined up next to each other, this can result in a cascade, right? This one's going to lose one, and it goes over to this one, which is going to be gaining one. That's not good. It'll lose one. Metals don't want to gain them, but that electron, when it goes over, does something that a metal does not like, right? It's going to gain those electrons. So this one makes that one lose, 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 and this can happen very rapidly, and this can be going on all the time, all over the metal. And this cascade is sometimes referred to as a mobile sea of electrons, but that just makes it sound like there's fuzzy electrons on the surface bouncing around. There needs to be a reason for it, and I think this can help explain that. This can also explain why metals are conductive, malleable, can form circuits, strong perhaps because of this distribution. It reminds me of resonance almost with organic substances. By delocalizing this difficult to deal with charge, it can help distribute it, it helps minimize it, and it can also provide strength. So that's metallic bonds. And sometimes they can form alloys, right? You can have metals of other elements that are within it or between it, right? And these are two types. We call these substitutional alloys. I think the word's helpful. It's substituted for another one. Or interstitial, which is just what it is. It's within the lattice there. And as you might predict, for these alloys, if you're simply substituting, oftentimes the properties are maintained somewhat. It can remain malleable and ductile. But for here, this can get in the way here, and so it can become less malleable or ductile. It's interfering with the normal pattern of things, and so these things can become less malleable, less stretchable, that sort of thing for the interstitial. That's an introduction to metallic bonds.